All right, so welcome today to in-person. Thank you for the accommodation. Go away. The accommodation on Monday. It was nice to see all of you that joined on Zoom. For those of you who did not, I will have that posted by this weekend, so you can go back and watch the first lecture video. Any questions from last time? So last time, for those that did already watch it or were there, anybody want to, what did you remember from last time? Willing to share? Anyone willing to share what you learned from last time? Oh, I thought I saw a hand, but no. Okay, go for it.
The difference between ordinary and extraordinary nodes, being ordinary nodes are two elements attached with a wire, and then extraordinary are two or three or more.
Great. All right. Did you have something different?
Yeah.
Okay, thanks.
We talked about series circuits and parallel circuits. The series circuits are connected by ordinary nodes, and parallel circuits are connected if the colors are the same on both sides.
Correct. Great. Great takeaways from last time. So if you didn't get those concepts from last time, make sure to go watch the video again, work through some exercises, make sure you understand those topics. Again, today we're going to review those, but those are really essential topics and concepts to be able to understand to move forward with the next material. So today I wanted to just backtrack slightly and go through a little bit about succeeding in engineering in general, since this is probably your first electrical engineering course. And for computer engineers, this is also, I call it electrical and computer engineering. So for both of you, I have seen a whole spectrum of students. I have been teaching here for 21 years, so I've been here a long time. So seeing a lot of different backgrounds, different cultures, so many differences between students. So no matter where you come from, you can succeed. I've seen students that were very poorly prepared, started out in 980 math, that went on to be successful. So 980 math, if you are not aware of that one, is even before algebra. So I have seen a student that did not have exposure to math or any background in math that was able to be very successful. And then I have seen really highly qualified students that come in with high AP scores, and still are not successful. So what makes the difference between a successful student, is there a question? I hear some talking. Is there questions before I continue on? No. Okay, thank you. So if you, success is kind of a perspective also. So a success means, are you happy for some people? Success may mean, did you actually reach your goals? So success is a very different perspective for everybody. So what I am going to define success as is being able to accomplish your goals. To me, that's what I'm going to term success. But each of you will have your own individual bias as to what success is. And so there are many resources and books on succeeding. So I'm not going to kind of talk about those. I would refer you to some other strategies as far as those books, resources. What I suggest is setting goals and continuously clarifying them. So to be able to do that, you're going to have three kind of types of goals. Some are going to be short-term, some are going to be intermediate, some are long-term. Hopefully all of you in here, being in here, have a little bit longer-term goal of graduating from our department. So with you even being here, I'm assuming that might be one of your goals. So to be able to do that, you need to really strengthen your own commitment of, this is really what I want. Some of you may be here for different reasons. And so you want to really think about and self-reflect on yourself, what is going to help you be more committed. And some of you may have barriers, and I have seen tremendous amount of students. So in our department, I don't think I mentioned last time, I'm also the director of our undergraduate and advising team. And so I've seen students, I've mentored students, very different, as I said, very different backgrounds, very differing cultures. And what I've seen is there's a lot of students that end up having barriers that are creating you from not getting to be successful. If you feel that you have barriers for some reason, I'm happy to discuss them. Our advisors are happy to discuss them. We have lots of resources available. And that is what I've seen be a really big hindrance to students, is to not identify that you have a barrier. And so you keep kind of stumbling, you aren't getting the successful grades that you want. So please note that our team is here to support each of you. I would love to see every single one of you not only get A's in this class, which each of you can do, but also be able to graduate through our whole program. So please do know I'm here as a resource. I'm here to happy to talk to you about anything, and be able to support you to do that. So set goals, strengthen your commitment, learn as much as you can about engineering. There's many different engineering fields, sub areas within electrical and computer engineering. And so making sure that you're aware as you can be about all of those. There's lots of opportunities we send. If you are not part of our ECE Canvas page, make sure that you do join that. If you have questions how to join, please contact me. And I can send you the link to get joined on that. We send out lots of announcements, lots of service opportunities, lots of research opportunities, lots of internship opportunities, lots of presentations. So all of those are opportunities for you guys to take advantage of. So highly suggest taking advantage of those. I understand time is also a huge commitment, and so that can be a barrier sometimes, is being able to have enough time. But as much as you can, learning about as many opportunities as you can. Prepare a roadmap. So some of you, that might mean meeting with an advisor, creating your academic plan. For others of you, that roadmap may be navigating your barriers, and how do you actually navigate around those barriers. So you have to self-reflect, what is your barriers, what does your roadmap look like, and what does that mean to you? So that's kind of generic, and you guys have to determine what that is. And then the last thing I like to say is believe in yourself. I believe in all of you. I know all of you are here. You want to be successful, and that as a teacher, I'm going to try and help you become successful by giving you information. But you guys have to act on it. You have to utilize all the resources. You have to ask the questions. I'm going to make assumptions, but I'm not always going to know if that really is what's going on in your mind. So please don't hesitate to voice questions or concerns. If you are not comfortable in this setting, please note that I'm available outside this setting and happy to meet with you more one-on-one if that's a preferred method. So a very quick summary. I'm going to provide a couple links on the Canvas page. One will be a chapter which I love that has more details about all these steps. And then there's a whole book on keys to succeeding in engineering, and I'll provide that link to that book. And so I did want to start off with that. In summary, pretty much, one thing you have to really know at the beginning is understanding your learning style. So on this, I've created this link. You can link to this on the QR code if you guys have a camera. I want to go on this really quick for a second. Make it a little bigger for anybody else. All right, and on this, there is the first link, as you scroll down a little bit, is going to be, everybody's done that, is going to be this ILS questionnaire. And so this will give you an online quiz that you can take to answer. If you haven't done this, some of you have already had 1900, may have done that in 1900 as extra credit. I again give it here as extra credit. So if you've already done this, that's great. You already know more about yourself. So with that, I would then suggest that you look at the learning styles and strategies. They give you tips and tricks that are helpful for your specific type of learning strategy. Once you are understanding of your own learning strategy, there's also a resource here on campus called the Learning Center, and it's over in the Marriott Library. You can set up a one-on-one consultation with a learning expert, and they are helpful in being able to give you additional expertise in your learning style to help you with navigating your courses successfully. So please utilize those. Don't know what just happened. There we go. Okay. So a couple other things that I want to mention. One is working hard. So I have had this conversation many times. So tell me if this like resonates with each of you at some point in your life. So ask a student, how's your semester going? How are your classes going? Oh, just fine. So, what's your hardest class this semester? Do you guys have questions? Thanks. So what's your hardest class this semester? One of them said like physics, and it's like, oh, great. So how are you doing in physics? Oh, fine. So, have you taken a test in there yet? Yeah, I just took a test. So what was your score? 53. Okay. So what grade, does that equate to? Did they curve it? I don't know. So, well, is it an A? Well, no, probably not an A. Is it a B? No, probably not a B. Is that a C? Probably a C. So, how much time are you spending? Oh, I'm spending 15 hours a week studying. Okay, so what did you do Sunday? How much time did you spend on Sunday? Oh, I haven't been able to study this week yet. So there's 2 days left of the week. So you're going to spend 8 hours each day studying. So this is some of the conversations that I've had. I don't know if this resonates with you or not, but is that working hard? Okay, so in my definition, that's not working hard. So work is also time. So lots of time. And then that gets me to the next point is working smart. So as I said, some of you may find, and it's very common at your age and stage of life, and I'm assuming majority of you are just coming in as young 20-year-olds, but there are maybe some of you not as traditional of a student. So working smart is going to be utilizing your time that you are spending very efficiently. So if you are hitting your head against the wall, knowing that you are capable of figuring it out at some point and that you just need to spend more time, but you keep spending time, you keep spending time, you keep spending time, and you have not gotten the homework done, that's not working smart. So working smart would be being able to self-reflect and identify oh, I am not understanding this. I have tried these resources. Maybe I've tried 1 or 2 or 3 options. Neither's working for me. Now it's time to utilize the experts, which are going to be me as an instructor and TAs. TAs are wonderful. We also have tutors that are available that are your peers that will be able to help you and give you a different perspective and help you understand it in a different way maybe. So sometimes one thing that I say may not resonate, but then a tutor may say it a different way, and that's what's resonating with you. Or a TA may say it a different way, and that's what resonates with you. So asking the same question from different individuals that are maybe experts in the field, at least if you've asked 3 different people, one of them hopefully will click with you. And so that's what I mean by being smart. Utilize your resources. That is one way to be really smart, is utilize resources. Don't hesitate to ask. That is one thing I do find, and especially with, I don't know if it was COVID, but it seems like if you had experiences during COVID with education, that you may not be as comfortable asking questions, and that's fine too. What you need to then learn is okay, that's not something I'm good at, so working with an advisor, working with a success coach, working with a learning center. How do I even ask questions? How do I even know how to ask questions? Sorry. So that is what I mean by being smart, is utilizing the resources that are available. Think positively. I think I kind of already addressed that, but a lot of it is attitude. Believe in yourself. Know that you can be successful. And then this is just kind of a summary from that book I was mentioning. 1, setting goals, strengthening commitments to your goals, and then changing negative attitudes. So this is part of that thinking positively, and changing non-productive behaviors. So that's what I mean by working smarter and more efficiently, is to identify what are those barriers and how can I be more productive. All right, any questions about my pep talk? Hopefully this was a pep talk of like, you guys can do it. Any questions? All right, we are going to move into the learning objectives for today. So already talked about tips for success. So next we're going to talk about understanding current, understanding voltage, identifying that ordinary and extraordinary node, and then we're going to go into applying KVL, KCL, and as part of that, identifying branches and loops. All right, so switch for a second.
Previously, we talked about how electric charges can build up on surfaces and create something known as static electricity. In this episode, let's talk about what happens when these electric charges continuously move in a process known as current electricity. Most electronics, everything from your refrigerator to your smartphone, requires current electricity to operate. Let's assume that we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated as amps and written with a capital A. 1 ampere is defined as 1 coulomb of charge moving past a point per second. Let's look at a cross-section of wire carrying an electric current. If it takes 3 seconds for 6 coulombs of charge to move through that cross-section, then we say that 2 amps are moving through that wire. Unfortunately, electric current doesn't just magically flow through wires. It needs a little help. If left alone, the electrons in a wire won't move. We need to give them a little push. To do that, we'll use a voltage source like a battery. In a battery, there is a buildup of negative charge on one side in the form of excess electrons. The other side has a buildup of positive charge, an absence of electrons in this case. The charges want to balance out, but the only way to do that is for the excess electrons to flow around the battery through a conductor that we provide. If we connect a piece of wire to the negative terminal, the electrons will push against the electrons in the wire. However, air is an insulator as its molecules do not have very mobile electrons, and it won't readily accept the free electrons. To show this, we'll put a piece of tape at the end of the tube. Now, the electrons at the end of the wire have nowhere to go. Even if we push against the electrons in the wire, they still won't budge. To fix this, we need to connect the other end of the wire to a place where the electrons want to go, and the positive end of the battery will happily accept the electrons. In fact, don't try this with a real battery. There is nothing slowing down or restricting the flow of electrons, which results in tremendous amounts of energy being transformed into heat in the wire, and this could easily melt the wire insulation or start a fire. This is known as a closed circuit, as it creates a loop from one side of the energy source to the other. If we break the wire or remove it from one of the terminals, then the electrons will stop flowing.
So for this, if this was an electric circuit, there's a battery and then there's an open wire. Is there current flow in that? There's not going to be any current flow. So this is what you're going to see on some of the circuit diagrams. There'll be this wire. It'll be kind of a dangling wire. It won't be connected to anything. Note that that means that there's no current flowing in that wire. And we're going to use that when we analyze circuits.
This is known as an open circuit. We've been talking about electron flow in a circuit and showing how electrons move from the negative terminal to the positive terminal. However, in electronics, we usually assign current as flowing from positive to negative, or from higher potential to lower potential. This is known as conventional current. In the mid-1700s, Benjamin Franklin theorized that positively charged objects had an excess of what he called electric fluid, and that negatively charged objects had a deficit of this fluid. Franklin noted that this fluid had a tendency to flow from positive to negative to distribute itself more evenly. It wasn't until the end of the 19th century that English physicist J.J. Thomson discovered the existence of the electron. Even though we now know that it is electrons that move inside of most circuits from low to high potential, the convention of current moving from high to low potential stuck. As a result, most current measurements are given as conventional current, which is the movement of positive charge in a circuit, and is represented by the capital letter I. Don't worry, the math still works out as long as we stick with either electron flow or conventional current. And since most electronics textbooks use conventional current, we'll go with that. We talked about making electricity do work for us, and the circuit forms the basis for all modern electronics, everything from the simple flashlight to massive supercomputers. If we made a circuit out of just a battery and a piece of wire, there's a chance we might melt that wire as the electrons move through that wire at an alarming rate and generate massive amounts of heat.
Okay, so all right, so any questions about that? I think that's a great visual to think of it as those little balls in the wire itself. So those are like atoms in a wire, and it's actually that movement of the push of the charge on one side that pushes through and moves in a hopping way through all of the atoms in there. And that's that electron movement that actually is the current. So this is thanks to one of our students. They actually did this experiment, and he sent me this photo, which is kind of fun. So this is an experiment if you want to do it on your own. So instead of hooking it directly up through a wire to the battery, which is going to melt it, you can put it through a potato and use the potato as a resistor. But in the potato, another effect happens where you can see a migration of some of the copper, and then you can tell like which side is positive and negative from that. It will bubble up, and so sometimes you can even see the movement of the electrons as it kind of moves through quickly, which is kind of a cool little experiment if you want to play around with that. So looking at current, so he mentioned conventional current, so that's what we're going to use, and when usually we use I for the notation of that current. And so if you are moving something that's just like a light switch that's connected to a battery, that would look like this. You have a light switch which turns on and off. Oh, that's large. And so you would model it schematically as a switch, and then a battery can be drawn, as I showed last time. There's a few different ways to model it. This would be another way to describe a DC volt, 1.5 volts. And then the LED, or the lamp, is going to be described by an LED. And so you could also rewrite this to look like this. And so an LED, this is a symbol for an LED, is the triangle with a line. And then the little arrows coming off that means that it's giving off light, so it will be an LED. So the LED symbol is with the two little wires. And then to connect this, if the switch is closed, then this would be, it would look like this. Internally to an LED is actually a little bit of resistance and an amount of voltage that needs to be used to actually turn it on. So this would be the schematic, and then we could describe the current, which would go, typically we'll draw it out of the positive side, so it would go in this direction, and we would label that as I, as the current flow in there. So this would be our electrical circuit for just a light and a battery and a switch. All right, so we're going to move into what we call Kirchhoff's current law, KCL. So what this says is that every current that comes into a node has to go out of the node, and they equal 0. So the summation of what comes in has to equal what goes out. So there's a few different ways you can say that. So if we have an ordinary node, that means that there's 2 elements, and the current going in is going to equal the current going out. That makes sense, right? Because there's only one wire, so whatever goes in has to go out. So even if it has a bend in the wire, that's what I was saying, it has to kind of go around that bend, and so it's going to be the same current. And it could also be something that has a lot of squigglies to it. So an element, you could have 2 elements like this, and the current in each of these small little wires is going to still be the same. It's going to still flow in the same direction. So this comes down to how do you like to look at this? So there's 3 different options of looking at this. If you look at this node, you can describe this node and define all the currents going in as positive, all the currents going out as negative. So that's one option. So this would be option 1. If you define that as currents going in, that would be a plus I1 plus I4, and then going out is I2 and I3. So that would be a minus I2 minus I3. That is all equal to 0. So that gives us that mathematical expression for the first one. Option 2 is that you could say that all the currents going in are negative, all the currents going out are positive. That's going to give you a negative of the first one. And option 3 is that all the currents going in equal the currents going out. So this one is probably more common for students to like this third option. But again, it's whichever way you like to do it. I would try maybe all 3 and just for you say this one makes the most sense to me. And then stick with that one the rest of the semester. So do that for a couple circuits and see which method you like and which one kind of makes in your sense to you in your brain, because everybody's going to be different. So with option 3, the currents going in are I1 and I4, and then the currents going out are I2 and I3. So that would be I1 plus I4 is equal to I2 plus I3. Okay, so we're going to try an exercise. Okay, I did not copy this link, sorry. So we're going to use the links from last time. So this is the same QR code and the poll everywhere. Maybe do it up here. I have lots of not gonna work. Okay. Okay, so introduce yourself to your neighbor, and then go ahead and try and find these values. Okay. Trying to do that. I cannot resize this window. Alright. I don't know what happened.
Where the sum of currents leaving the node and returning to the node. They're not equal to each other. I'm going to draw this diagram.
Okay, one more minute. Okay, great. It looked like you guys were able to get the same answers, which is always nice to see consensus. So as far as the equation set, note that each of these is an extraordinary node. And a branch is going to have the same current in it. So this is a very key concept too, is that the current stays the same in a branch. A branch is a connection between two extraordinary nodes. So in here, I see that this element is connected between node 1 and node 4, which are both extraordinary nodes, so that's a branch, which means the current going through it is only one current. So if I have two currents labeled in there, they have to equal each other. So that's why I1 equals I7 in there. So I1 equals I7. And then again, depending on what you like as far as how you write this, if your currents go in equal your currents going out, or your currents going in are positive, currents going out are negative, or the opposite, currents going in are negative and out is positive, you could write the different node equations. So for node 1, if I do, this is a description of those going in as positive, those going out. So this is option 1. Another way to write that would be I1 is going in, and so that equals I2 plus I3. So this would be option 3. So those are different ways of writing the same equation. You can see mathematically once you write it, you can manipulate it into any other form. And so, sorry, you can't see those. So first one, option 1, I1 goes in, I2 and I3 go out. And then the option 3 was that goes in has to equal what goes out. So I1 equals I2 plus I3. For node 2, you have I3 comes in and I4 and I5 go out. So the summation at node 2 is, I'm randomly picking option 3 because I have written here also the other options. So I3 goes in is equal to I4 plus I5. And node 3, summation of currents is going to equal I5 that comes in, I2 comes in, and then I3 goes out. So it will be I2 plus I5 equals I6. And then the last node, node 4, summation of currents, is going to be I4 comes in and I6 comes in, and then I7 goes out. So those would be the summation of current equations, and then manipulating them algebraically, and you come up with the answers that were shown there. 42 milliamps for I1 and I7, 30 milliamps for I3, and 12 milliamps for I2. Any questions on this current law? Okay, great. All right, we're going to move to voltage. So with voltage, going back to our diagram with the battery and the lamp, there's a voltmeter that you would put, it has a positive probe and a negative probe. And in the lab, this will be red, and this one would be, typically it's black. So with those probes, you can put them across an element. And remember I was saying to highlight the colors of each wire between elements. So this would be one color, and then this would be a color. If I put the positive on this side and the negative on this side, what would I measure?
Excuse me,
Yes.
is a switch not an element?
So a switch is not an element. Thank you for asking that question. So what you're going to look at for the switch is what position is the switch in. You could have two different circuits, and you're actually going to redraw the circuit depending on what stage the switch is in. So you don't treat it like an element, you treat it like either it's a wire or it's open. And then the circuit will be drawn based on what timing you have with it. Does that make sense? Thanks for asking that. All right, so if I was to measure the plus probe here and the minus probe, that's going to measure,
Oh, negative 1.5.
thank you, because then positive is actually connected to the negative side of the 1.5 volt battery. So with this orientation, it's going to measure a negative 1.5. If I swap that and did a positive this side and a negative that side, with this one I'm going to measure what? A positive 1.5, thank you. Okay, so it depends on the orientation of which way you put those probes on of what you're gonna measure. All right, so we're gonna back to voltage.
To understand how electricity works, we need to zoom in on atoms, the things that make up all matter. Atoms are made up of three basic particles. That is, protons, which have a positive electric charge, neutrons, which have no electric charge, and electrons, which have a negative electric charge. The protons and neutrons are tightly packed in the core or nucleus of an atom, while electrons move about this nucleus in regions known as shells or orbitals. Right now, this atom is electrically neutral, as it has the same number of protons and electrons. With enough energy, an electron may be stripped away, leaving the atom with a net positive charge. Likewise, another atom may receive a freed electron, which then makes the atom electrically negative. When we have two objects with different electric charges due to the absence or presence of excess electrons, we say that we have static electricity. We can demonstrate this using a balloon and a soda can. When I rub a piece of cloth against the balloon, I strip away electrons from the piece of cloth and add them to the balloon. As a result, this balloon now has a net negative charge. When we bring it close to the can chases the balloon. Let's look at why that's happening. The aluminum in the can is a conductor, which means that the electrons can freely move about the material. As we bring the negatively charged balloon near the metal, the electrons are pushed away to the far side of the can, since like charges repel. That leaves an excess of positive charge on the side of the can nearest the balloon, which is pulled toward the balloon as opposite charges attract. Since the positive charges are closer to the balloon than the negative charges, the attractive force is greater than the repulsive force. This results in a net force that pulls the can toward the balloon. Let's see that again in instant replay. Before we go any further, let's talk about units. The SI unit for electric charge is the coulomb, generally abbreviated with an uppercase C. An electron has a charge of about negative 1.602 times 10 to the negative 19th coulombs, and a proton has a charge of about positive 1.602 times 10 to the negative 19th coulombs. Energy is usually given in joules, which is abbreviated with the symbol uppercase J. 1 joule is equal to the amount of energy transferred to an object when a force of 1 Newton is applied to that object over a distance of 1 meter. Energy can either be potential, which results from an object's position or arrangement, or kinetic, resulting from the object's motion. Both kinetic and potential energy are given in joules. Now we can define voltage. Voltage is a measure of electric potential between 2 points. The unit, volt, is defined as 1 joule of potential energy per unit charge given in coulombs. Let's explain this with an example. Let's say that I've got a particle with a negative 1 coulomb of charge. Then, let's say there is a particle with positive 1 coulomb of charge next to it. Since opposites attract and the positive particle is as close as it can get to the negative particle, everything is at rest. There is no kinetic or potential energy. Now, Let's say that I need to use 10 joules of energy to move the positive particle from its resting position to this point. If I were to release it, it would move back to the negative particle. As a result, we can say that it has 10 joules of electric potential energy so long as I hold it here. Now, if I repeated this demo with 3 positively charged particles, it would take 30 joules of energy to move them the same distance away from the negative particle. So, they have 30 joules of potential energy as long as I'm holding them here. As we defined earlier, voltage is the electric potential between 2 points. To calculate the voltage between their starting and ending points, we know that I did 30 joules of work to move the particles, and the total charge is 3 coulombs. So the voltage is 30 joules divided by 3 coulombs, which is 10 volts. We would say that the electric potential between these 2 points is 10 volts. If I released one of the particles, it would move back to the negatively charged particle. That would leave me with 20 joules of potential energy and 2 coulombs of charge. So the potential is still 10 volts. Even if I had no positive particles, the potential between the 2 points is still 10 volts. As you can see, electric potential energy is not the same as electric potential. When we start talking about moving electrons through conductors and electronic components, we are talking about current electricity, which is slightly different than static electricity. Let's take a look at a battery. It doesn't really matter how far apart the terminals of a battery are. The chemicals inside a battery determine the electrical potential between the terminals. A fully charged AA alkaline battery is listed as having 1.5 volts. That means each coulomb of charge moving from one end of the battery will do 1.5 joules of work. Now, compare that to a much larger D-cell battery. Each coulomb of charge will still only do 1.5 joules of work, but a D-cell has far more coulombs of charge than a AA. As a result, D-cells will last a lot longer than AA batteries, doing the same amount of work. Static electricity can be a lot of fun, but more often than not, it's considered dangerous or a nuisance. One of the most dramatic displays of static electricity happens in nature. Storm clouds can build up a potential difference of millions of volts when compared to the Earth. And at some point, the electrons actually force their way through the air, creating lightning in order to balance out that charge difference. This sudden flow of electricity in an attempt to neutralize 2 statically charged objects is known as electrostatic discharge, or ESD. While lightning is a rather extreme display of electrostatic buildup and discharge, static electricity can still be quite useful. For example, many factory and power plant smokestacks employ a technology that uses static electricity to pull soot and ash out of the air as it flows up through the pipe, resulting in less pollution. Also, most cars are painted using a process called powder coating. In this, paint leaving the spray nozzle is given an electric charge, and the car body is given a different electric charge, which creates a stronger bond between the paint and the car body. This allows for a more uniform paint coverage and reduces paint waste, since less of it's likely to stick around in the air or drip off the car body. Next time, we'll dive into current electricity and talk about...
All right, so we'll go back to the voltage. Voltage for next class time, and then we'll move also into some new topics with power and Ohm's law. All right, any questions before we're done? Okay, so again, there was also a question, like, again, no labs this week. Labs will start next week, and then no homework due this week. All right, see you guys on Friday.